All right, let's go over this warm-up. So for each of these pairs of triangles, we want to say whether they are congruent or not. Number one, these two triangles right here, are those two triangles congruent to each other? Yes. Using which postulate from first semester? Side, side, side. So I would say yes by side, side, side. Side BC is marked as congruent to FE. AC is marked as congruent to FD. And AB has those three markings on it, so it is being marked congruent to DE. That is why we have side, side, side. What about on number two? These two triangles here, are they congruent to each other? No. Why not?
Because they have all the congruent ones are on their own triangle.
Yes, all the congruent signs are on their own triangles. So on triangle XYZ, all three of those sides are marked as being congruent, but just to each other. On triangle RPQ, we have congruence marks, but they are distinctly different than XYZ. So they're all congruent to each other. Speaking of, though, if I have a triangle with three congruent sides, what does that mean about the three angles? They would all be the same. How many degrees does a triangle always add up to? 180. So if it's 180 degrees for a whole triangle and all three angles have to be the same, how big is each angle? 60 degrees. So angle R is 60 degrees. So is Q. So is P. Because we have the same situation for X, Y, Z, X, Y, and Z are also all 60 degrees. So it's not that they have nothing in common, but angle, angle, angle does not prove congruence. What about number three? These two right triangles here, are they congruent to each other?
Yeah.
Yes. Using which congruence postulate? Side, angle, side. So HL can only be used with right triangles, so I love that people saw that. But in order to use HL, we have to have congruence information about the hypotenuse. The hypotenuse is always going to be directly across from the right angle. So this side right here, KL is my hypotenuse, and that doesn't have any congruence markings on it. That's why I'm not allowed to use HL on this particular problem. So always check the side that is across from that right angle. If there's no markings, we can't use HL. Nice work on the warm-up. Go ahead and put your warm-up page away for today. And we're going to be just in your extra notes packet today. We won't be in your book at all today, but we will tomorrow, so please make sure you bring it with you. In your extra notes packet, we're going to be on the back side of the second page, so page 4. Yes, sorry, it's the very bottom one right there. There you are. Yep, no worries. No worries. I've got extras. Yes. For that one? Okay, when we hit the D lunchtime, I'll pull out the answer key so that you can finish correcting that and turn that in. Page 4, back side of the second piece of paper. Should say 8-2 similar polygons up at the top. So in 8-1, we talked about dilating figures, and when you dilate a figure, you end up with a similar figure, and we've talked about similar figures. Now we're going to talk a little bit more about how do I know if two figures are similar? If they don't tell me that they're dilated, I just have two shapes that look kind of like each other, how can I tell if they are similar figures? So we're going to start off with a definition. Polygons are similar if and only if when I say if and only if, that means that everything that comes after it has to be true. If some parts are true and other parts are false, then they're not similar figures. There are two criteria to be similar figures. Corresponding sides have to be proportional. So if and only if corresponding sides are proportional, and corresponding angles have to be congruent. In order to be similar, both of those have to be true. So if they ask me to figure out whether or not two figures are similar, it has to meet both of these criteria. And I am going to ask you about this later on in the lesson, so please make sure that you are coming back to this definition when I ask if those figures are similar, or when I ask what criteria have to be met in order for figures to be similar. All right, before we actually get into finding out whether or not figures are similar, I want to practice a little bit with what we've done the last couple days. We are assuming that these two pentagons right here are similar. I want to find the scale factor for both the enlargement and the reduction. Scale factor is what over what? Yes, new over original. So if I'm doing the enlargement, I would have to go from the smaller one to the bigger one. What would my fraction for my scale factor look like? (2.25) over 1.5. That's absolutely correct. Can somebody pop that in their calculator for me and tell me what you get when you do 2.25 divided by 1.5? 1.5. So in simplified form, I would say that the scale factor for the enlargement is 1.5. Or if you wanted to leave that in fraction form, but you wanted it in simplest terms, that would be 3 over 2. So there's our enlargement. For the reduction, I would be going backwards. How does that affect my scale factor? We flip it. So now it's going to be 1.5 over 2.25. What is that when we pop it into our calculator? 0.6, and then it stops? Keeps going. So 0.6 repeating, or we could write that as the fraction 2 over 3. One more thing I want to touch on with you guys before we actually start answering some questions, and that is how to read a similarity statement. Do you guys remember when we had our triangle congruent statements? You had like triangle ABC is congruent to triangle DEF. And those congruent statements are telling you a lot of information. They're telling you which angles are congruent to which other angles. It's telling you which sides are congruent to which other sides. A similarity statement is very, very similar. It works almost the exact same way, except instead of telling me about congruent sides, it's going to tell me about proportional sides. So down here on number 3, this little squiggle that is in between the two figure names, this means similar. And when I have two similar figures, and it's written as this statement with the squiggle in between, the first letter in each of those figure names, so A and W, they're telling me that those two angles are corresponding, and so they would be congruent to each other. So angle A is congruent to angle W because of the way that congruence statement is written. That's going to be true for every letter in its position in this similarity statement. So B is the second letter here, and X is the second letter in this other name. So I know angle B is congruent to angle X. Can somebody give me another pair of angles that are corresponding and therefore congruent?
Angle C and angle Y.
Absolutely. Angle C and angle Y would have to be congruent to each other. I'm going to go and mark that on my picture. Here's angle C. Here's angle Y. And are there any other angles that are corresponding and therefore congruent? D and Z, last one in each name. Angle D congruent to angle Z. So those are my congruent angles. My proportional sides. Remember, when we set up a proportion with the sides, if my figures are similar, that tells me the scale factor. And the scale factor should be the same for every pair of corresponding sides. So my similarity statement is going to tell me which sides are proportional to each other. So first two letters in this first name is AB. Let's go find side AB. Right here is side AB. First two letters of the other figure name is WX. WX would be this side right here. Because they both fall first in their names, first two letters, those two sides are proportional to each other. So I would have AB over WX. Those sides are corresponding and therefore proportional to each other. That proportion is exactly the same as every other pair of corresponding sides. And again, I'm going to look at this similarity statement to figure out which sides are proportional. Middle two letters, BC. And then in my other name for my figure, middle two letters is XY. So BC over XY. Before we go any further, I want to talk about how I have set these fractions up. It does not matter because they didn't tell me which of these two shapes was my original and which was my new. It doesn't matter which figure I have in the numerator and which figure I have in the denominator. Because of the way the similarity statement is written, because of the way my figures are here on the page, I decided that the sides of my smaller one were going to go in the numerator and the sides of the larger one would go in the denominator. But we could just as easily do it the other way around as long as you stay consistent. If you put WX in the numerator, then XY has to go in the numerator, YZ has to go in the numerator, and WZ would have to go in the numerator because those are all coming off the same figures. If you put those in the denominator, then they would all have to go in the denominator together to stay proportional. All right. We've got two of our proportional sides. Can anybody give me another side, or a pair of sides rather, that would have to be proportional because they're corresponding? CD, last two letters, and YZ, last two letters. So CD over YZ. I've gotten to the end of my similarity statement names. We've talked about side AB. We've talked about side BC. We've talked about side CD. Which side have we not said anything about yet? AD. We didn't say anything about that. Well, when I look at the name of that polygon, A is at the beginning and D is at the end. So I'd be looking for the same kind of pattern in the other figure's name to know what it's proportional to. So AD would have to be proportional to what? WZ. Nice work. All right, let's take what we started this page off with and everything that we've done in between. Let's bring that together, and we're going to determine whether or not some figures are similar. Number 4, we want to determine whether the polygons are similar. And if so, if they are, then we're going to find the scale factor for both the reduction and the enlargement. We wrote down at the top of the page the 2 requirements for figures to be similar. What are those 2 requirements? In order for figures to be similar, what 2 things have to be true? Corresponding sides have to be proportional. And what else? Corresponding angles have to be congruent. The 2 required criteria for polygons to be similar to each other. We have to have proportional sides. We have to have congruent angles. So let's go back and look at our 2 figures here. I'm looking at this, part A. I usually check for corresponding congruent angles first, because usually that's more of a visual check. I don't have to set up any fractions. I don't have to reduce things. I don't have to grab my calculator. Do we have corresponding congruent angles between these 2 figures? Yes. Angle B is congruent to angle K. Angle C is congruent to angle L. Angle D is congruent to angle N, and angle A is congruent to angle J. So we have corresponding congruent angles. So that meets one of my criteria right there. What's the other criteria again? Corresponding sides have to be proportional. So when I say they have to be proportional, I'm going to have a fraction that's equal to some other fraction. I don't know right now whether or not those are equal to each other. We're going to have to do a little bit of work to figure out whether or not corresponding sides are proportional. Before we set up these fractions, we have to decide, is the little parallelogram going to be in our numerator, or is the big parallelogram going to be in our numerator? Let's do big. Sounds great to me. Does it matter which one you pick? Nope. You can put the small one in the numerator. You can put the big one in the numerator. Does not matter as long as you stay consistent. How many sides do we know about on that big parallelogram? We only know about 2 of them, right? Or at least that's what's labeled on the picture for us. It has 4 sides, but we only have lengths for 2 of them. We got to pick one of these 2 to write one of our fractions. Do you guys want to go with the 20 or the 40 first? 20 sounds good. So 20 is going to go in the numerator of my first fraction. And in the denominator, I need the corresponding side on the other parallelogram. 15. Nice work. So 20 over 15 would be one of my fractions. I have to write another proportion for the other pair of corresponding sides. What will that fraction look like? 40 over 30. If I knew about a third set of sides, I would have to write a third proportion, because these fractions all have to be equal. If I knew about all 4 sides, I would have to write 4 fractions and make sure that they all come out the same. The easiest way for me to tell if these 2 fractions come out to be the same thing is for me to pop it in my calculator and see what the decimals are. So can somebody put 20 over 50 into their calculator? 15, sorry. Thank you for correcting me. 20 over 15. 1.3, is it repeating? 1.3 repeating. Now we have to do the same thing with 40 over 30. Same thing, we get 1.3 repeating. So these did come out to be exactly the same when we put it into our calculator. That tells me that corresponding sides are proportional. So that meets my second criteria. Since it met both criteria, what does that mean about these two parallelograms? They are polygons. They are similar to each other. What we were checking with those criteria is whether or not they were similar to each other. So our polygons, polygon is just a fancy word for most of the shapes that you're familiar with. Squares, hexagons, pentagons, rectangles, all of those are polygons. The polygons are similar. The directions said if my polygons came out to be similar, then I had to find the scale factor. And I had to find it for the reduction and for the enlargement. We've already found one of them. You guys remember back here when we put those two fractions in our calculator to check to see if they were the same? What we came up with, 1.3 repeating, that is a scale factor. Would it be for the enlargement or for the reduction? Why for the enlargement? You're absolutely correct. It's in the numerator. Yep. There you go. The other way we can tell is because when we put it in our calculator, we got a number that was bigger than 1. 1.3 is a little bit bigger than the whole number 1. So that is my scale factor for the enlargement. 1.3 repeating, or if you wanted to write that in its fraction form, that would be 4 over 3. There you go. Scale factor for the reduction. You're absolutely correct. Would have to be 3 over 4, which we can see if we switch our fractions around from the beginning, 30 over 40. That simplifies down to 3 over 4. Or does anybody know what that would be in its decimal form? 0.75. All right, part B, we're going to check the same thing. Check to see if these two figures are similar. What are the two criteria to check for similarity? Absolutely correct. Corresponding sides are proportional. Corresponding angles are congruent. Look at the two rectangles that we have in part B. Are the corresponding angles congruent to each other? How big are those angles? They're all 90, right? They all have the little boxes in the corner. Is 90 equal to itself? Yes. So every single angle in here is congruent to every other angle because they're all 90 degrees. All angles are equal to 90 degrees. So that means between the two figures, the corresponding angles are congruent because 90 is equal to 90. So we've met our first criteria. Second criteria, I have to see whether or not those sides are proportional to each other. I only know about two sets of sides, two pairs of sides. So I'm only going to be able to write two fractions. But remember, if it tells you about 3 sides, you have to write 3 fractions. If it tells you about all 4 sides, you have to write 4 fractions. Decision time. Do we want the big one or the little one in our numerator? Big one sounds good. You want to do little one this time? Sure, why not? Let's do little one in the numerator this time. It doesn't matter which way you do it. Since we did big on top last time, let's do little on top this time. So little rectangle first. I have one side that's 3 and one side that's 8. Which one do you guys want to go with? 3. So that's going to go in my first numerator. When I look at that rectangle, the side that's 3 is my short side, right? So what would that have to correspond to on the other rectangle? Has to correspond to 16. So 16 would go down in my denominator. What should my second fraction look like? 8 over 32. And now's the part where we grab our calculators. What's 3 over 16 when you put it in the calculator? You said 1875? So 3 over 16, if it leaves it in decimal or in fraction form. I really want to change it into decimal form for this because it's hard between these two fractions for me to see if they're going to come out the same. But when I put them in decimal form, I can absolutely see if they're the same. What about 8 over 32? 0.25. Did they come out to be identical? No, they did not. So that tells me that the corresponding sides are not proportional. So what does that mean about these two rectangles? What were we checking to see? The polygons are not similar. That's absolutely correct. And for space, I'm going to use the symbol for similar instead of writing that word out. Polygons are not similar. We're going to flip the page and do just a little bit more. So we still have 14 minutes, technically. We're going to do at least number 5. We might push on and do number 6. On number 5, it tells me that triangle ABC has been dilated. If I know one figure has been dilated to create the other one, that means they have to be similar. So triangle ABC is similar, squiggle, to triangle DEF. Which one would have to be the original this time? ABC, because that came first. So I'm going to add that to my figure. This is my original. It said ABC was dilated to create DEF. So this thing came second. That means it is my newer shape. So was this dilation an enlargement or a reduction? Enlargement. My original one was the little one. And what happened when I was done was I got a bigger one. So it was enlarged. We need to find the scale factor for this. Scale factor is what over what? New over original. Well, when I look at my new triangle, it tells me about 2 different sides. I have a 20 and I have a 30. But only one of them has corresponding information on the other triangle. 20. 20 is corresponding to what on my original triangle? 8. So 20 over 8, or what would that be if I put it into my calculator? 5 over 2, or 2.5. Do I care whether it's a fraction or a decimal? Nope. Make sure for repeating things, though, that you are putting the repeating symbol. So 5 over 2, or 2.5. We're going to use that scale factor now to find the two sides that we have no information about. So side BC is going to be the first thing that we find. I don't know how big side BC is, but I know that scale factor is equal to new over original. And we just figured out the scale factor is how big? 2.5. So 2.5 is equal to, what's the corresponding side to BC on my new triangle? EF, 30. So I'm going to put 30 in my numerator. Do we know how big side BC is? Nope. So I just have to leave this BC in my denominator. We're going to figure out how big it is. We solved a similar problem to this the other day. BC is part of a fraction right now, but I want to get BC by itself. That's what it means to solve for it. If I need to get it alone, I don't want it to be down on the bottom of a fraction. What operation did we talk about yesterday undoes fractions? Multiplication. If you do it to one side, you have to do it to the other side of the equal sign. And to get rid of a fraction, we always multiply by which part of the fraction? Denominator, the bottom. What's on the bottom of this fraction? BC. So we're going to multiply by BC. I know. That's why we're talking about it. We don't multiply by the 30. It's not the number that we multiply by, it's whatever's on the bottom. If there happens to be a number on the bottom, then we multiply by a number. In this case, it was a variable. All right, so I have 2.5 that's getting multiplied to BC. That's over on the left-hand side. And on the right, the only thing I have remaining is 30. .5 doesn't equal 30. 2.5 times BC. Remember, we multiplied these things together, but I want to get rid of that 2.5. What operation would undo the multiplication that's there? Division. So I'm going to divide both sides by 2.5. And now I can pop this into my calculator. 30 divided by 2.5. 12. So side BC is 12 units long. Add that to my picture. What's the other side that we're supposed to find? DF, this side right here. Scale factor is equal to new over original. Scale factor is 2.5. Is DF part of the new triangle or part of the original? New, so it has to go in my numerator. DF has to go up on top. What side does it correspond to on the other triangle? 10. So I'm going to put 10 down in my denominator. DF is part of a fraction. I don't want it to be part of a fraction if I'm trying to solve for it. What operation undoes fractions? Multiplication. So we're going to multiply both sides by what? 10. It's always whatever is on the bottom. So 10 times 2.5 would give me 25. We are going to do problems 6 and 7 tomorrow. So we're going to wrap it up for today. Your homework that you picked up on your way in the door is due on Friday. We learned how to do some of it today. We're going to learn how to do similar but slightly more difficult problems tomorrow. Yes, absolutely.